Artemis 2, Infrastructure for Humanity's Multi-Planetary Future. The Artemis 2 mission represents far more than a nostalgic return to lunar exploration. Scheduled for no earlier than 2025, this 10-day circumlunar voyage embodies a fundamental shift in how humanity approaches space exploration, from flags and footprints expeditions to building sustainable infrastructure for permanent human presence beyond Earth. By examining the mission's technical architecture, crew composition, scientific objectives, and international partnerships, we can understand how Artemis 2 serves as the critical bridge between our planetary past and multiplanetary future. Unlike the Apollo program's singular focus on lunar landing, Artemis 2 functions as a comprehensive systems validation mission for deep space infrastructure. The Space Launch System, SLS, generating 8.8 million pounds of thrust, surpasses the Saturn V's capabilities while incorporating modern manufacturing and safety systems. The Orion spacecraft, with its European-built service module, represents genuine international hardware integration rather than mere diplomatic cooperation. The mission's figure-8 trajectory around the Moon, extending 230,000 miles from Earth and passing 4,600 miles beyond the lunar far side, isn't simply about distance records. This fuel-efficient path leverages gravitational dynamics to test long-duration life support systems, deep space navigation, and crew performance under conditions that future Mars missions will encounter. The trajectory design reflects a mature understanding of propulsion economics that Apollo-era engineers could only theorize about. The Artemis 2 crew selection transcends technical qualifications to embody a carefully orchestrated vision of 21st-century exploration. Commander Reed Wiseman, pilot Victor Glover, who will be the first person of color to travel beyond low Earth orbit, mission specialist Christina Koch, bringing extensive ISS experience, and Canadian Space Agency's Jeremy Hansen represent not just professional expertise, but strategic messaging about space exploration's evolution. This diversity isn't performative, it reflects the reality that sustainable space exploration requires global participation and varied perspectives. The inclusion of a Canadian astronaut particularly signals the program's reliance on international partnerships for critical components like the Canadarm3 for the future Gateway Station. Each crew member brings specific competencies: Wiseman's leadership experience, Glover's test pilot precision, Koch's long-duration spaceflight record, and Hansen's representation of international collaboration. The mission's scientific objectives reveal sophisticated planning for permanent lunar presence. Rather than collecting samples, Artemis 2 focuses on three critical areas that enable sustained exploration: astronaut health studies, the Archer, Avatar, and immune biomarker investigations go beyond basic medical monitoring. Using organ-on-chip technology and comprehensive biometric tracking, these studies aim to understand how deep space radiation and microgravity affect human biology at the cellular level. This data directly informs countermeasure development for the multi-year Mars missions that Artemis enables. Operational lunar science: the 3-hour lunar far-side passage transforms astronauts into real-time geological observers. Their training in terrestrial analog sites like Iceland prepares them to identify and document features invisible from Earth, impact crater morphologies, volcanic flow patterns, and potential resource deposits. This observational capability becomes critical when selecting landing sites for future missions targeting in-situ resource utilization. Space weather characterization: with 24/7 monitoring from NASA and NOAA, Artemis 2 will encounter and document the deep space radiation environment firsthand. The international CubeSat deployments from Germany, South Korea, Saudi Arabia, and Argentina create a distributed sensor network, each investigating different aspects of the radiation environment. Germany's Tacheles examines electronic component degradation, while Korea's K-RAD Cube uses tissue-equivalent dosimeters, practical research for protecting both humans and equipment. The ground infrastructure supporting Artemis 2, the mobile launcher platform, upgraded vehicle assembly building, and modernized Launch Complex 39B, represents multi-billion-dollar investments in permanent capability rather than mission-specific hardware. The Deep Space Network's upgrades for Artemis enable communication infrastructure that commercial operators can leverage, creating economic multiplier effects beyond government programs. This infrastructure approach reflects learned lessons from the Space Shuttle and ISS programs. Sustainable exploration requires systems designed for decades of operation, not just individual missions. The emphasis on modularity, reusability, and commercial compatibility positions Artemis as a platform for economic development rather than purely scientific exploration. Artemis II's significance lies not in replicating Apollo's achievements, but in fundamentally reimagining humanity's relationship with space. By prioritizing infrastructure development, international collaboration, and scientific understanding over pure exploration, the mission acknowledges that becoming a multiplanetary species requires more than courage and rocket fuel. It demands the patient construction of systems that make human presence beyond Earth inevitable rather than exceptional. The mission's success will be measured not by the images of Earth rising over the lunar horizon, but by whether it enables a continuous human presence that our children will consider as natural as transcontinental flight. In this context, Artemis II represents humanity's first serious attempt to build the infrastructure that transforms space from a destination we visit into a place we live.